All right, this is video number 2, and we're following up from video number 1. So far we've only discussed moles, mass, and molar mass. So you know now moles, mass, and molar mass. Okay, those are the three things you know. You know that's measured in moles, this is measured in grams, and this is measured in grams per mole. Okay, so that's what you know so far. All right, but what happens if we're dealing with a compound? Do the same rules apply? So the answer is yes. However, you need to remember that your calculations will apply to the whole compound. So when you calculate molar mass of a covalent compound, you'll need to add the masses of the atoms. The number of moles will also apply to the whole molecule. For example, so I could have 1 mole of nitric acid. So here's some new things I'm going to be mentioning. When I talk about, there's 2 types of things. There are common names and there are chemical names. And those common names and chemical names have formulas. So nitric acid, the formula is HNO3. All right, so I can have 1 mole of nitric acid. All right, and I can say, if I wanted the molar mass of nitric acid, HNO3, I can calculate that because I know now that it's going to be 1 plus 14 plus 16 times 3, and my molar mass of HNO3 is going to be 63 grams per mole. If it's a whole number, you can leave it as a whole number. That means, therefore, there's only 1 mole of it. Therefore, there are 6.022 times 10 to the power of 23 molecules of nitric acid. We're not looking at specific atoms, we're looking at molecules. I can do the exact same thing and I can say 1 mole. Please make sure you're getting these examples into your book. So 1 mole of salt, that's what we call the common name, which is sodium chloride. And this is the chemical name. All this is ringing a bell from grade 10. And the formula is NaCl. 1 mole of NaCl has a molar mass, so we say NaCl is equal to 23 plus 35.5, and we've done this calculation before, is going to give me 58.50 grams per mole. Just have a look there. When I've got a decimal, we want to make sure it's rounded off to 2 decimal places. Okay. So that means, therefore, there are 6.022 times 10 to the power of 23 molecules of sodium chloride. In 1 formula unit. Okay. All right, so when we look at ionic compounds, we use in 1 formula unit, right? And when we use molecular covalent compounds, we use molecules. So covalent, that's the statement we're going to use. And this is the statement we use for ionic. So please make sure you get that sorted out. So when I'm looking at a basic equation, a chemical equation, you need to make sure you understand how this works. So let's have a look at what we mean by when we're dealing with compounds. So let's say I had N2 plus H2, which is NH3. And at this point, you should be able to tell me if they're gases, solids, liquids. All right, so in here, this is not balanced. So what I want to do is I'm going to balance it. And what we're going to do is we're going to put a 2 there, and we're going to put a 3 there. All right. Now, in words, in this reaction, okay, we need to be able to understand how this works. So in this reaction, we have 1 mole, okay, 1 mole of nitrogen molecules reacts with 3 moles of hydrogen molecules to produce 2 moles of ammonia molecules. Now, where am I getting these numbers from? So I want you to have a look here. When we balance an equation, we put in here coefficients. So here, in front of the nitrogen, I have an imaginary 1. In front of the hydrogen, I have 3 moles. And in front of the ammonia, I have 2. So this 1, 2, 3, these numbers, these coefficients that we use, they are the moles. So it's important for us to understand this. You know by now how to name a compound. You also know how to write a balanced equation. You also know how to determine whether it's single displacement, double displacement. You know all of that because you've done chemical change. But now what you need to understand is what these coefficients mean. If I have a coefficient, that coefficient tells me how many moles I have. If I have a coefficient of 1, it is not necessary to put in the 1. Okay? But if the coefficient is greater than 1, then we must put in those coefficients. So how I would read it in words is 1 mole of nitrogen reacts with 3 moles of hydrogen to give me 2 moles of ammonia. That is how we read these reactions. So when we're talking about coefficients, we're talking about a mole of a molecule, number of moles of a compound, number of moles of an atom, for example. So coefficients are moles. That's how it's read. Please make sure you get this into your book. It's very, very important because your questions are going to come across and use the word moles. They're not going to use the word coefficient. You're going to be lost. Right. Let's have a look at an example. So they give me an example. Let's say example 1. They say calculate the molar mass of H2SO4, which is sulfuric acid. At this point, you should be learning your names of your acids. As we go through, you'll get used to it. And then eventually, it's not something I'll have to remind you about. All right, so you go M, H2SO4. Please make sure you are subscripting. And you've got 2 hydrogens. So you've got square brackets. 2 times 1 plus 1 sulfur, and sulfur is 32, plus 16 times 4. You have 4 oxygen molecules. And all you have to do is pop that into your calculator and you get 98 grams per mole. And the periodic table we're using here when I'm doing these calculations is the periodic table without the decimals. If you do use the periodic table with the decimals to do these calculations, that's fine too because you're practicing. The reason why I'm using the one without the decimals is because that's the one you'll get in any kind of exam. All right, example 2. It says calculate the number of moles in 1 kilogram of magnesium chloride. Okay, now here's your first problem. We cannot work in kilograms, so we need to work in grams. So you need to do that conversion. So if I was looking at mass, 1 kilogram is times 1,000 grams over 1 kilogram, and that should give me 1,000 grams. There's my conversion. Nice and easy because it was a round number. But in exams, please make sure you must convert. We do not use kilograms in chemistry. We only use grams. they give you kilograms, it has to be in grams. So you've got the mass here. They want number of moles. We don't know that. And we're going to need the molar mass of MgCl2, which we can work out quickly. Your magnesium is 24 plus your chlorine, which is 35.5 times 2. So just pop that into your calculator, and your molar mass of magnesium chloride is 95 grams per mole. Alright, so I've got my information. Now I've got to put it into my formula. I go N is equal to little m over big M. The little m is 1000 and the bigger M is 95. So 1000 divided by 95, put into your calculator, and N is equal to 10.53 moles of MgCl2 is present in 1 kilogram of the sample. Get used to statements in chemistry. Same thing with kinematics. It says in the direction of motion, things like that. In chemistry, we also write these statements out. The next topic we're looking at is composition. Now, when we talk about composition, we're talking about what are compounds or molecules made of. Right, and what we're looking at here is we're looking at ratios. So in order to do that, there are three things that we look at. The first thing we look at is the percentage composition. Okay. The second thing is something we call the empirical formula. This is new. And the last thing we look at is something called the molecular formula. Okay. Now, knowing either the empirical formula or molecular formula of a compound can help determine the composition in more detail. Composition meaning what are the compounds made of. This is the opposite is also true. If we know the composition of a substance, we can find its formula. Right, so there are 4 different types of composition problems that you might come across. I'm just going to give them to you so you have a better understanding of these things. All right, please make sure that this gets into your books. I'm just going to go through them. The first one you'll be given the formula. And then you will be asked to calculate the percentage by mass of each element in the substance. You're going to be given the percentage composition and asked to calculate the formula. You can also be given the products of a chemical reaction and calculate the formula of one of the reactants. Right? This is usually with combustion reactions. And then you're going to be able to find the number of moles in waters of crystallization. I'm going to explain each of these. I'm going to give you an example of each one so that you can understand how these are going to come across in your tests or exam. Please make sure you write these down because what comes after this is each one of these problems. Okay, so the first example is calculating the percentage mass or percentage by mass of elements in a compound. Okay, so the question is calculate the percentage that each element contributes to the overall mass of sulfuric acid. And that's H2SO4. Okay. So the first thing you need to do, there are steps, right? Step number 1. The first thing you need to do is you need to calculate the molar mass. Okay. So what we do is hydrogen, there is 2 times 1, which means there's 2 grams per mole. Then you've got sulfur, which is 32 grams per mole. And then you've got oxygen, which is 16 times 4, which then gives you 64 grams per mole. And we've already worked this out. So therefore, we're going to use that previous question. Therefore, the molar mass of H2SO4 is equal to 98 grams per mole. Okay. Once you've got the molar mass, the second thing you need to do, step 2, there's a formula we use. This formula is not on your formula sheet. You have to memorize it. So please write it out neatly, nice and big, and then highlight it. So we say percentage by mass is equal to the atomic mass. Now your atomic mass is each individual's mass, right? Atomic mass over the molar mass. So your atomic mass here is in grams per mole of your atom or your molecule that's part of this compound. And this is also in grams per mole. And we take that whole thing and we times it by 100. And that is your formula. This answer you're going to get here is in percentage. This formula, again, is not on your formula sheet. You just have to know it. All right, so we do each, step 3, we sort out each individual atom. We've got hydrogen here. We say the percentage is equal to 2 divided by 98 times 100. You've then got sulfur. The percentage is equal to 32 over 98 times 100. And you've got oxygen, which contributes 64 grams per mole over 98 times 100. So all you got to do is pop each of these into your calculator and get the answer. So pause the video and do it yourself. Alright, so if you put it into your calculator, you would have gotten these 3 values. Hydrogen was 2.04%, sulfur 32.65%, and oxygen 65.31%. Now, when I'm looking at those values and I add them up, that value must be as close, or rather, let's say, the percentage must be equal to plus minus 100%. So you need to get as close to 100. That's how we check our answer. So when you check your answer, so the reason my answer is 99.99 because I rounded off to 2 decimal places. Okay, and when I do that, I'm cutting decimals. When I cut decimals, I end up cutting whole numbers as well. So if we kept all the decimals, and you would have seen on your calculator, they were huge decimals. We round off to, you can keep these in 2 decimal places. And what that does, it cuts it down. So you want to get as close to 100 as possible. If you get less than 100, so if you get, for example, 96 or you get 80 something, then means something's wrong with your calculation. So please make sure that when you do this, you are as accurate as possible and you check your answer. So we call this part here a check to see if you are sorted out. Again, what I'm substituting in over here as my numerators, that is the molar mass of the total that atom contributes. So I can't just say hydrogen, because when I'm looking at the formula, which is H2SO4, like that, I've got 2 hydrogens, I've got 1 sulfur, and I've got 4 oxygens. So I'm not putting in just the molar mass of hydrogen or just the molar mass of oxygen. I'm putting in the molar mass of its contribution to sulfuric acid. So hydrogen contributes 2 atoms and oxygen contributes 4 atoms, while sulfur only 1. If it's 1, it's fine. If it's 2, you're going to mention 2. If it's 3, 4, 5, whatever the case is. That is how you do percentage composition. All right, so what I've done here is I've given you 5 examples, right? I've done the answers for you. What you need to do is you need to do what I've just done here. So you're going to do this over here for every single one of these. But I've given you the answers so that you can check if you were correct. You will round off to 2 decimal places. Please don't forget that. If there are no decimals, you can leave it as a whole number. But there's a few here. Ammonium sulfide, you're going to have to find the formulas for these. So you need to go back to your table of cations and anions. If you don't know it, go over it again. It's ammonium sulfide, aluminium acetate, sodium bromide, copper 2 hydroxide, and magnesium carbonate. Those 5. I want you to do this calculation here that you're seeing, that I just did with you. Write down the name of the compound, find the molar mass. Your formula must be there. So you get a mark for that. You get a mark for substituting each time. And then you get a final mark for each of your answers. So work out your molar mass. You get a mark for that. Work out your molar mass of each compound. So what you're going to do for each one, you need to find the name of the formula. Okay, whatever it is. So if it's ammonium sulfide, you need to find the formula. You need the formula because if you don't have the formula, you don't know how to work out the molar mass. Then you need the molar mass. Then you need to write down the formula. You write down the formula only once, even though you're doing the calculation 3 times. Then for each element, you calculate for each element. You want each element's percentage. You show all work. Okay? And then the last thing you need to do is you need to do your check. Right? For all 5 examples. You need to check if your answers correlate with that. So 1, 2, 3, 4, 5 steps for 5 examples. Again, ammonium sulfide, aluminium acetate, sodium bromide, copper hydroxide, magnesium carbonate. So what you need to do now is pause the video, do the exercise, mark your work. Okay? If you don't understand something, you send me a message on Teams and I will try and help you out. Alright, so please do that before you move further into this video. Alright, the empirical formula. The empirical formula is a chemical formula showing the simplest ratio of elements in a compound rather than the total number of atoms in the molecule. So if I had something like glucose, okay, its molecular formula, this is what we call the molecular formula. It's your common formula that you know. That is glucose. But the empirical formula has to be the simplest ratio of elements. So if I look at all the coefficients, they're all divisible by 2. By 6, sorry. So I've got CH2O. And that is the empirical formula. Now when they give you the empirical formula, what they give you is they give you information, right? So what they do is you are given the percentage mass contribution of each atom. Of a compound. Okay? And what you need to find is if they bond, what's the simplest ratio in which they can bond? Okay. So again, there's a whole lot of steps that need to be taken in. we need to make sure that we understand this whole setup. The first thing you need to understand is if I have a compound, okay, each atom's contribution must be in total 100%. Okay, so when we add up each percentage of each compound, I must get 100%. That's the first thing. The reason for that is when I'm working with these, finding the empirical formula, my sample size must be 100 grams. Okay, so we can see a link here. If the percentage contribution has to be 100%, then the sample size must also be 100 grams. It means that the first thing we have to do is we got to convert the percentages into grams. Okay, now that's very easy to do if the sample size is 100 grams. The only way the sample size is 100 grams is if the percentage is 100%. So what you're going to do first is you need to make sure that your percentage composition is equal to 100%. Then you've got to go from percent into grams, and that will give you 100 grams. That's your conversion. That needs to happen first. So before you start with any of these questions, you need to make sure that whatever they've given you gets to 100%. In an exam or a test, we will make sure it's 100%. If it's not at 100%, and let's say it's at 98%, or it's at 99%, that's fine too. Right? It's fine. It's just off by a margin. That's fine. But usually in an exam or test, we make sure it's 100% so you don't have any kind of error. If it's far away from 100%, then it is not possible to do the calculation because then you don't have a 100-gram sample. All right, so let's look at the first example. Again, remember, you need to make sure you pause the video. Pause so that you can take down the notes. Everything that's in this video needs to be in your book. I cannot stress that enough. All right, let's see. Example 1. A compound contains 52.20% carbon, 13.00% hydrogen, and 34.8% oxygen. The question is determine the empirical formula. Okay. All right, the first thing I need to do is I need to do a conversion. So what I like to do is I like to draw a table. Right? So you can draw the table. I find that it works wonders. And make it an open-ended table. You'll work across the table. So I'm just going to draw a table quickly. Okay, this is the table that I'm drawing. So what I want to do in my table, and I like this method because it's kind of foolproof and you can keep all your calculations in one place, right? So you've got carbon, you've got hydrogen, and you've got oxygen, all right? So the first thing you were given was the percentage. Please watch how I label this table because if something's missing, SI units and stuff, I cover the bases here. So I don't have to worry about them. So they gave you 52.2%. They gave you 13% of hydrogen. Okay. And they gave you 34.8% of oxygen. When I add that together, I get 100%. So that's my first thing that I need to sort out. The second thing they want is mass. And I put a G here so that I don't have to sort that out. Now, if it comes to 100%, the conversion from percentage to mass, because the mass is going to be 100 grams, for your mass, it's the same. So we'll fill in the mass, has 52.2 for carbon, 13 for hydrogen, and 34.8 for oxygen. So now your masses are sorted out. Right. Next step you need to do is you need to find the number of moles. Okay, so you put that in brackets. And what I do here is I write my formula one time. I need to show all working out, but I don't have the time to write the formula every single time, so I put it in the heading of the table so it refers to the whole kind of setup. All right, so here for the first one, for carbon, I need my mass of carbon, which is 52.2, divided by my molar mass of carbon. Now my molar mass of carbon is 12. Okay, sort it out. Hydrogen, it's 13 divided by 1. Okay, and oxygen is 34.8 divided by 16. Okay, so what I've got here is my percentage mass, and divided by the molar mass of the atom. All right, what happens now is, please make sure you do not include diatomic, because I know I have hydrogen and oxygen at diatomic. We do not include that. We're finding the simplest ratio of when they bond. All right, what you want to do is you need to put that into your calculator, and you need to get the number of moles for each of these. And so if I put this into my calculator, I'm going to get 4.35. And I don't have to put the SI units because I've put it in my column. If it's not here and you miss it out here, you're in trouble. All right, 13. And over here, I should get 2.175. Okay. For this answer here, please hold as many decimals as possible. I'll explain as we go on. The decimals is what affects everything here. Right. Now what you need to do is you need to find the ratio. You need to find the ratio. Right. So what you're going to do is, to find the ratio, I'm just going to put it here on the side so you can make a note for yourself. Right. To find the ratio, you take the moles of the element and you divide it by the smallest number of ratios. That's the formula. All right, so all I write here is, and there's no SI units, you divide by the smallest ratio. Now the problem comes in with the decimals. You're going to find a situation where they're similar, but they're different by the fourth or fifth decimal. That matters to us. It must be by the simplest ratio. So if I'm looking at all of these ratios here, the one I can identify as the simplest ratio is 2.175. So all I do is I take each of my ratios, so 4.35 divided by 2.175, I go 13 divided by 2.175, and I go 2.175 divided by 2.175. All right, so what I do then, in my third column, that's going to give me the simplest ratio. Oops. Okay, I'm just going to zoom in. You should have the notes that are on the side. So if I put 4.35 over 2.17, I get 2. If I take 13 divided by 2.175, I get 6. And if I get 2.175 divided by 2.175, I get 1. Now this ratio is what we've been looking for. this is what we need. So we say now, once you've got that ratio, we say that when carbon, hydrogen, and oxygen bond with each other, the simplest ratio they form is C2H6O. Where am I getting these ratios you see here in this column? They become the subscripts of the empirical formula. Okay, so therefore, the empirical formula for carbon, hydrogen, and oxygen is C2H6O. Now you get marks right through here. Okay, you get marks for converting here. Get a mark for your formula, for each type of substitution, for dividing each by the ratio, for finding the actual ratio, for writing down the empirical formula. So this table is a foolproof way to keep you can do all the calculations out of the table if you want. I find that when you use the table, all your working out stays in one place. All your SI units stay in one place. So I don't need to keep writing down the SI units for every single calculation. Right, so you need to make sure to keep your calculations together. For example, if I didn't do it in the table, then every answer must say mole. This must say mole. If it doesn't say mole, right, then I'm in a situation where I'm going to lose the marks for substitution. So please make sure you get 1 mark here for all your moles being correct. Right, it's a hefty question, 7 marks, 8 marks, depending on what they're asking you. Please make sure that you're following through. I'm going to do a few more examples with you. Please pause the video, try and do the calculations yourself, read the question, do the whole table, and then come back and press play and see if you're on track. Do not just copy blindly from these videos. They will be of no use to you later on. There's no time for us to keep coming back here. So try and do as much of the calculations by yourself as possible. All right, for the second example, it's a little bit different. So we're just going to have a look here. This time, instead of giving you the percentages, they're giving you the grams. So they're telling you that your sample is 60 grams. Now we don't have to worry about it being 100 because we're not working with percentages. A 60-gram sample of tetraethyl lead, a gasoline additive, is found to contain 38.43 grams of lead, 17.83 grams of carbon, and 3.74 grams of hydrogen. Find its empirical formula. Please make sure you write down the questions before you do the calculations, right? So the first thing I want to do is I want to fill in my table. I want to put in lead, carbon, and hydrogen. Now, a lot of you are going to ask about the order. The order in the question is the order of the formula. Don't mix it up. Keep it in that same order. And so normally we put your percentage. I do this every single time and they haven't given me percentages. The second thing I have is mass, which is in grams. See, I put my SI units in. They gave me 38.43, 17.83, and 3.74. And when I add all of those three things together, I should get 60. That's my sample. Now, they didn't give you percentages, so this time our sample is 60 grams. Doesn't really affect anything, but you don't have to worry about it being 100 because they're telling you what the sample is. It's not 100 grams because you're not working with percentages. So if they don't give you percentages, you work with the sample that is given to you. All right, the second thing that needs to be done is you need to find the moles. Again, SI units and a formula, always. Okay, just make this a bit bigger. All right, so I've got here, for the first one, I need to make sure that I have in front of me my periodic table because that periodic table is just going to assist me here. So the mass is 38.43 divided by the mass of lead, which is 207. They've given me 7.83, which is of carbon. That's divided by 12. And 3.74 divided by 1. So all you got to do is now pop that into your calculator, and you can get your ratios out. And so the first one you've got is 0.1856521739. I'm trying to keep as many decimals as possible. For the second one, it's 1.48388. Sorry, 3333 and so on. And for the last one, it's 3.74. All right, the next thing you need to find is the ratio. So first, to find the ratio, you need to identify your smallest ratio. And in this one, your smallest ratio is this one. So everything needs to be divided by that. So you've got 0.1856 divided by 0.18565. Try and hold your decimals. 1.488333 divided by 0.18565. It's easy if you hold it on your calculator as well. Then 3.74 divided by 0.18565 and so on. All right, the next thing you need to do is you need to get the ratio. Okay. Right, now for this ratio, if I look at it, I'm going to get 1 there. All right, but for the second one, I'm getting 8.016. And for the last one, I'm getting 20.145. Okay, so what I want now with these ratios is I want to round off always to the nearest whole number. So I'm showing you different kinds of scenarios. Different scenarios have different problems, right? So over here, my ratio then, my simplest ratio is 1, 8, and 20. So my empirical formula, therefore, and keep it in the order, is PB C8 H20. That is my empirical formula for this type of setup. All right, so please make sure you check these. The problem there is when there's a 5, so if it's at 8.5 or it's at 20.5 or even 1.5, then the whole thing changes. There's a whole new method of working things out. I'm going to show you one like that. All right, next. Okay, this question over here. You have a 170 gram sample of an unidentified compound contains X, Y, and Z. And let's just have a look at that, how this is going to work. Okay, so the first thing I want here is my 3 things. It says sodium, so Na, chromium, Cr, and oxygen. I keep it in the same order. So over here I would have had percentage. I write it down, I get into good habits. The minute I start skipping things, it gets out of control. They've only given you grams here, so we're going to work with the mass. Okay. They've given you 29.84 grams of sodium, 67.49 grams of chromium, and 72.67 grams of oxygen. And that should give you 170 grams in total. Once that's sorted out, you can start moving to the next thing. Please make sure you take down the question so that you know what you're doing when you're doing the working out. Please try and pause for certain sections. This one, the ratios, it's going to be a little bit different, but you can do this first part by yourself. All right, you need moles here and your formula. Okay, so you've got 29.84 divided by 23. Then you've got 67.49 divided by your mass of chromium, which is 52. And then oxygen 72.67 divided by 16. So pause the video, get this calculation, and then see if you're on the right track. Okay, so when I'm looking at this, those are my values. I need to identify the smallest one. And of these, I must look at those decimals. They're almost identical. Right, so I want to choose the smallest ratio. So 2973, 2978. So this is the ratio I'm going to be dividing by. So I've got 1.297391 over 1.297391. Got 1.29788646 divided by 1297391. And over here I've got 4.541875 divided by 1.29391. I try and keep as many decimals as possible, but if you don't keep all, that's fine too. I pop that into a calculator and see what you get. Alright, so over here for the first one, you should have gotten 1. The second one, you would have gotten 1.00037, whatever the case is. And for the last one, you should have gotten 3.5007. Alright, now here's the complicated part. When I'm looking at my ratios, and any of my ratios are a 0.5, I cannot just round off to the next whole number. So make a note here. If it's 0.5, if there's a 0.5, you cannot round off to the nearest whole number under any circumstances. This is NB. What you have to do is you have to multiply by a factor. And what we do is we want to get the 0.5 to the next whole number. Okay, so the best thing to do with that is to always multiply that. Well, not always. In this case, to get 3.5 to a whole number, I want to multiply it by 2. So I'm going to go to each ratio and multiply by 2. Right, so now my simplest ratio has changed. Right, 1 times 2 is 2. This number here could have been rounded off. So that's going to be 2. And this number now is 7. So we need to get it to a whole number. Whatever the 0.5 number is, you need to get it to a whole number. It's not necessarily always going to be 2. Sometimes it's going to be a different number. That's fine. You need to multiply it by whatever factor. You cannot round off. If you round off, you're going to get the wrong empirical formula. All right, so the empirical formula for this one, right, is going to be Na2 Cr2O7. Now, if you didn't round it off, you would have had NaCrO4, and that is incorrect. That is not even a thing. So please make sure that when you're doing this, there are different rules, there are different things going on. You need to pay attention to the theory behind it when you're doing these types of calculations. All right, so this is the end of video number 2. You need to move on to video number 3. Again, these videos are lengthy, but they have a lot of information that you need and a lot of work that you can do by yourself. When we get back to school, we'll do more of these examples and exercises. Right now, you need to make sure you get all the notes done. So please make sure that you're not spending hours and hours and hours just watching these videos one after the other. Watch a video one day, skip a day, watch another video, and so on and so on. Don't try and cram everything into one day. It's just too much of information. And please make your way to video number 3.